So hello, thank you. It's really a pleasure to be here today. I'm just really impressed with the panel and everyone. You have a really deep set of knowledge accumulated on this call today. So it's great to hear and learn from. I'm here to discuss a fundamentally new approach to clean hydrogen production. We call it a new wave in hydrogen production. Because we use shock waves to heat natural gas, and it's essentially a new energy paradigm in methane pyrolysis. See if I can get it to move. And it doesn't want to advance. Hold on. Why won't it work? Okay, now it's going. All right. So as you all know, the overarching goal is decarbonization or the reduction of greenhouse gas emissions. And we need to do this quickly. I think everybody recognizes that it needs to be implemented on. Are you hearing a feedback?
No, we're hearing just fine.
All right, thank you. Needs to be implemented on a very large scale in order to really forestall the cascading effects of climate change. So as showcased here today, one solution is transition to a hydrogen-fueled economy. But there are significant barriers in that transition that need to be overcome. So these are a few of the barriers. Our technology addresses these barriers. I'm hearing a major echo, which is...
Yeah, it's not carrying over with us, so you'll just have to, I guess, bear with it. It might be your headset.
All righty, no problem. So as you know, the current state of the art is steam methane reforming, or SMR, and over 90% of the world's hydrogen is produced via this method. But what isn't often known is that it also produces a good degree of CO2, and it has a high water demand. To rectify this, sometimes SMR is linked with carbon capture and storage, CCS, which is a good solution, but it adds other limitations. For Alberta, as example, you're lucky to have the Alberta carbon trunk line. You have CO2 pipelines in place, and you have a CCS storage area, but many areas in the world, or even in Canada, don't have that infrastructure in place. So for SMR to become a low impact technology or greener or blue hydrogen production, it would require a parallel build out of CO2 pipelines and many different new storage infrastructure programs. And this is a really high cost, it's high risk, and it's going to take at least 10 to 20 years or more to have a significant impact. Due to the timelines and build out. So what we suggest is a fundamentally new approach to methane pyrolysis. I call our process a new energy paradigm because we don't need electricity to drive the reaction. We use the pressure inherent in a pressurized natural gas pipeline to drive the shock wave. So it's an efficient use of energy, and it can heat the natural gas to temperatures high enough to directly crack the methane molecule into hydrogen and solid carbon. And these are both valuable products. But as you can see, there's no water and no CO2 in the equation. This is a new application of wave rotors. Wave rotors have been around for about 50 years. So it's very low risk in terms of development. We're using a core component that's been known for 50 years. And in fact, all of the components in our process are standard and patented innovation is the novel application. So we use wave rotors to achieve gas temperatures sufficient to directly crack methane into hydrogen. So it's a new use of this technology. Wave rotors envisioned as a rotating barrel of shock tubes with end plates that have ports in them. And when a closed port aligns with one of the shock tubes and we introduce a pressurized gas, the gas reflects off that closed port in a enclosed space and creates a shock wave. So it's kind of a supersonic speed that compresses the gases and transfers heat. So we amplify the temperature of the natural gas. We have tremendous global partners, and which was launched from Canada, starting a 2-year program, and hope to achieve a field pilot by the end of 2023. This 2-year program is funded both by industry and agencies in Canada as well as in Europe. Some of the partners on the call today and some of the agencies mentioned are actually partners on our team. AMTA and the ACE program are doing the hydrogen fuel truck trials, along with the transition accelerator and CESA. They've been tremendous partners, and we're really excited to be working with them as well as everyone else. The NGIF is a natural gas innovation fund, the combination, a consortium of the natural gas producers and distributors in Canada. They're a co-founder of ours. Total in Europe is also a co-founder of ours, as well as GRT Gas, the major natural gas producers in Europe. We've been co-funded by ERA, the Emission Reduction Alberta, and we have a So if you look at Canadian, European, and US hydrogen roadmaps, they emphasize 2 major production methods: SMR with CCS in this line, and electrolysis. Those are the 2 that are focused on in the hydrogen roadmaps the most. But as I said, there's barriers inherent in each of these technologies that actually slow the transition. And what we think we've done is create a technology that addresses these barriers. So we're accelerating the hydrogen transition. SMR, as we discussed earlier, it produces CO2, or it has a high CCS risk. It's a very mature technology that has a low cost, but mostly at large scale. When you look at small scale distributed systems, such as those that will be needed for hydrogen fueling stations, for example, SMR gets fairly expensive. For electrolysis, it doesn't produce any CO2, and neither do we, but it has a really high, typically, electricity demand. So that electricity, yes?
If you want to maybe move to your last slide, and we'll quickly go to a quick question period.
Thank you. Okay. So in essence, really the key to our differentiation is that we can use the existing infrastructure, the natural gas distribution infrastructure. We don't need any new CO2 pipelines. We don't need any new hydrogen pipelines. We don't need carbon capture and sequestration. We use what's already existing to move the transition forward in a very quick manner. And it's the same with export. We don't need new types of ships or types of transition, chemical transitions to the hydrogen, because you can export the natural gas the same way we do right now and export the technology to produce hydrogen on demand wherever you have a pressurized pipeline. Okay, these are some of our end markets.
Okay, thank you. And then we'll just I'll just put Slido on, and then we've got a couple questions. So let me just bring them down to where you're at. So part of it is, what's the percentage, just an idea of the amount of energy used, and I guess what's the how does this kind of hydrogen production compare to some of the other methods in the amount of CO2 and energy?
Okay, so the purity, screen, the purity can be as high as 3 nines, 99.999, or 4 nines. In certain designs, we have different designs for different applications. So if we are admixing into a pipeline, like the ATCO project was referred to earlier, we only need 20% of the hydrogen conversion to go to the pipeline. We can have a high purity 20%, or if we're going into a fuel station, we'd have very high purity, and we polish it using a pressure swing absorber, a PSA system. The energy required is very low, again, because we don't use electricity to drive the reaction. It's a shockwave driven reaction based on the pressure drop. We can install in any pressurized pipeline and use that letdown or that drop in pressure to drive the process.
Okay.